In this example, we're asked to plot a frequency distribution of a bunch of density measurements. So in this table, we're given that we have 20 different measurements of the density of some glass particles. So you can see the various measurements that were made. And we're asked to plot a frequency distribution of the density values with the x-axis ranging from 1800 to 3200 kilograms per cubic meter. You'll see if you look through here, that range puts bounds on this data. None of this data falls outside that range. And we're told to use 7 total bins so that each bin size is 200 kilograms per cubic meter. The choice of the bins is just to make the plot look reasonable and give you some reasonable bin sizes to work with. A lot of times, if you do this using software, the total number of bins and their bin size will be chosen automatically by the software to give you sort of an optimal looking plot. We're also asked to find the sample mean of the distribution and determine the true mean of the particle density with a confidence interval of 95%. And then lastly, we're asked to find what fraction of these density measurements lie within this range from 2200 to 2800 kilograms per cubic meter. So the first thing we're going to do is find the frequency distribution. And if you recall, a frequency distribution looks something like this. Just sketch it out. On the horizontal axis, we'll have the density measurements, and these will be in kilograms per cubic meter. And then the vertical axis will be the frequency with units of 1 over the density. So this will have units of 1 over kilograms per cubic meter. And typically these plots looks, something like that. Okay, we're going to look at the exact form of it in just a moment. The other thing is the area under the frequency distribution, the area under this curve should equal 1. So if you integrated that up, the area would be equal to 1. Okay, so let's work this out for our particular case. So the first thing we'll do to find the frequency distribution is we'll work from the histogram or the counts of the various numbers. So what I mean by that is the frequency within a certain range. Let me just put it xi to xi plus delta xi. So the frequency of samples within that range of xi to some other value will be the number of values in that range. So the number, this is the counts, how many of the measurements are in that particular range, divided by the total number of measurements, divided by the bin size in that range. This is the delta xi, that's the same value here. So let's do this for our particular case. We'll do it for a few bins. So let's do the frequency distribution, or the frequency value, for starting with 1800 to 2000. Okay, so this is in kilograms per cubic meter. The reason I'm choosing this range is because we're told to start with 1800 and to go in bin sizes of 200. So that gives me 1800 to 2000. So then we need to get the count of how many values are in that range. So when I look through here, so 1800 to 2000, when I look through it, there's 0 actually. So this will be 0 over, well, here we have a total of 20 measurements. So 0 over 20, and then our bin size here would be the 200. We were told here that each bin size should be 200. So, it's the 1800 to 2000 is 200. So this would be over 200 kilograms per cubic meter. So obviously that frequency comes out to be 0. Okay, so let's do the next one. Frequency from 2000 to 2200. And by the way, just to be a little more precise, I'm going to choose my bins actually on the left-hand side. They're going to be equal to 1800 and equal to 2000, and then on the right-hand side it'll be just less than 2000 or just less than 2200. That way there's no ambiguity on how to handle the edge points. Okay, so from 2000 to 2200, when I look through here, I'll highlight all the ones that fall within that range. So 2000 to 2200. So I see 2003, and I think that's it. So we just have 1. So we'll have 1 over 20, and our bin size is 200 kilograms per cubic meter. So that will be 1 over 4,000, which comes out to be 0.00025, 1 over kilograms per cubic meter. So that's my frequency for that range. Let's do one more. So we'll go from 2200 up to 2400. Again, I'm going in bin sizes of 200 as specified in the problem statement. So let me highlight those in a different color. Let's use an orange color. So 2200 to 2400. So there's 1, there's 2, 3, 4, 5, 6. Okay, so now we have 6 counts over a total of 20 counts. And again, our bin sizes are 200 kilograms per cubic meter. So if I plug in the numbers for that, which I did on a piece of paper, it comes out to 0.0015, 1 over kilograms per cubic meter. So that, and then we can continue that for the rest of the bins. So that's the idea of how we get these frequencies. And then once we have those, we could make a plot similar to what I had shown up here. And when I do that, I just did this numerically in a computer program. When you do that, you get a plot that looks like this. So here's the frequency on this axis. You can see the units are 1 over kilograms per cubic meter. Here's the density, kilograms per cubic meter. And my bins actually go from 1800 to 3200 as specified in bin sizes of 200. You can see that each one of these has a width of 200. And the first bin, the frequency we calculated came out to be 0, recall. So that first bin size, the frequency was 0. The second one was 0.00025. So let's come back here. So you can see this at 0.00025 is right there. And then the next one was 0.0015, which you can see is right here. So these are the 3 that we just calculated. The black line here is still the same frequency distribution. All I did was just plot it showing the points at the center of the bin. So you can see, again, our bin sizes are 200 kilograms per cubic meter. And so the middle of the bin will be right there, for example, at 2100 kilograms per cubic meter. It's just a different way to plot it. You don't have to do it both ways in general. I just wanted to show it 2 different ways. One showing the actual bins, and the other one just showing the center of the bins. So that is our frequency distribution. And if you calculated the area under this curve, you know, the area of all these blue bins, for example, the area should equal 1. That's the way frequency distributions work. Okay, and the way I did this numerically is I actually wrote a Python program, and that's given in, I'll show it on the screen here, but I have a solution for this that also includes this code. I'm not going to step through all of the parts of the code that's outside of the scope of the solution, but I'll just say that, you know, here, this command here just shows the all of the data. And then as far as the plotting of the histogram, let me go down and try to find it here. Here we are. Yeah, so to plot the histogram, it's this command right here. Plot, this says histogram, but this is actually frequency distribution. A histogram would just be a plot of the counts versus the density. So how many density measurements are in the given bin range. But when you put density equals true in this command, it makes it a frequency distribution. It actually converts it from a histogram into a frequency distribution. So that's the command, let me highlight it, that actually plots the frequency distribution. And the key flag here to go from a histogram to a frequency distribution is that density equals true. If you want to get more information on this, you'll have to look up the documentation on this command hist for Python programming. Okay, so I won't get into the details here. All right, so that's the frequency distribution. Let's see, let's go back up to the problem statement. We're also asked to find the sample mean of the distribution, and then the true mean with a confidence interval of 95%. So let's do that next. So the sample mean is just 1 over the number of measurements, and then we sum. It's the standard way that we make mean value calculations. So it's just that calculation where we take the sum of all the measurements, n is the total number of measurements. So each measurement, we add them together and divide through by the total number of measurements. So we're just adding up this entire column and then dividing through by 20. So that's all that is. It's kind of our standard way of doing it. And if you work that out, you'll get a mean value of 2484.8 kilograms per cubic meter. So that's called the sample mean. And the reason it's called the sample mean is because what we've done is we out of the entire population of glass particles, we chose 20 of them to get our mean value. Right? So that we didn't take the entire, world's distribution of glass particles, some huge quantity of glass particles, and found the mean for all of them. We're just choosing a small sample of 20 of them and getting the mean from that. If we wanted to calculate the sample standard deviation, it would look like the following. We weren't asked specifically to do this calculation, but here's how you would get the sample standard deviation. So it would just be taking each measurement, subtracting out the sample mean, square it so that you don't have to worry about plus or minus, divided by 1 times n minus 1. This is called the number of degrees of freedom. And you take the square root of it. So that's the standard way of calculating the sample standard deviation. If you do that calculation, just so you have it, that comes out to be 201.9 kilograms per cubic meter. If you wanted to calculate the standard error of the sample means, we'll call that SEM. By the way, I'm showing you all these because these are building up for us to determine what the true mean is. So to get the standard error of the sample means, that's given by sample standard deviation divided by the square root of the number of measurements. So when you plug in this value, so we just calculated S, the number of measurements is 20. This comes out to be 45.2 kilograms per cubic meter. Now the reason we want this is because if you watch the lecture on the statistics of multiple sample experiments, this standard error of the sample mean is the breadth of the distribution of sample means. So for example, here I have one trial where I've made 20 measurements. But let's imagine I did this again. I chose 20 different particles and did another trial. And then I chose another 20 particles and did another trial and just did this a bunch of times. So I have a whole bunch of sample means, right? So I have all these trials, each one with a sample mean. The breadth of that distribution would be the standard error of the sample means. Okay, so that's what that is. Now to get the true mean I'll just represent as mu. That will be the sample mean plus or minus, we have, we'll call it the t factor, a 95% confidence interval, times the standard error of the sample means. And that t factor depends on how many measurements we actually have. And you can look this up in a table or look it up online, but the t factor for a 95% confidence interval with n equal to 20, so we have 20 measurements. So the t factor depends on how many measurements you have. So for 20 measurements, that comes out to be 2.093. So that's the value we would plug in here, and then the standard error of the sample mean goes there. And of course, the sample mean goes there. So our true mean will be 2484.8 plus or minus at 2.093 times the 45.2, that comes out to be 94.5 kilograms per cubic meter, and that's to a 95% confidence interval. So the true mean of our glass particle density will be somewhere in that range, to within 95% confidence. It doesn't mean 100% confidence, but we're really, really confident that the true mean of the glass particle density is in this range. Okay, so that's that part of the problem. The very last part is what fraction of the density measurements lie within the range of 2200 to 2800. Okay, so what fraction lies within that range? So let's go back down to this plot. What we're trying to do is find out what fraction of measurements lie within, let me show it on the plot. We said 2200 to 2800. So what fraction of measurements lie within that range? So the way we can find that is, for a continuous distribution, what it looks like is the following. If we integrated from 2200 to 2800, the frequency distribution within that range, that would be the fraction in the range. (2200 to 2800). So that's how that would work. It's basically the area under the curve between 2200 and 2800. Remember that the area under the curve over the whole frequency distribution should equal to 1, because 100% of the measurements are within that whole range. We're just trying to find out what fraction are in this range. So what we're going to do for that is we're going to just take our plot here, and you can see that our frequency from 2200 to 2400 is 0.0015. We calculated that previously, so it's 0.0015, 1 over kilograms per cubic meter. So that's, again, just from 2200 to 2400, and then we multiply that by our bin size. That's the dx. Dx is our little distance along this axis. So our dx here is 200 kilograms per cubic meter. So this is, again, from 2200 to 2400, and then we'll do the same thing from 2400 to 2600, and you can see the frequency is the same value, 0.0015. And the bin size there is exactly the same, 200 kilograms per cubic meter. And then lastly, we'll go from 2600 to 2800, and that's the exact same value from our frequency distribution. It just so happens, for the data that I provided, those frequencies are all the same. So again, this first one, let me highlight it in orange. That one is this one right here, so I'll highlight it there like that. And the next one, I'll highlight that in yellow. That's the middle one, is this one. And then the last one I'll highlight in kind of a light blue. This one from 2600 to 2800, and that's this last one. So we can plug in the numbers for that, and when you do that calculation, it comes out to be 0.90. There are no units to it because you can see that the 1 over kilograms per cubic meter cancels out with that. It's a fraction in that range, so the fraction should be, it should not have any units, and it should be equal to 1. It should be somewhere between 0 and 1, which indeed it is. So 90% of our measurements actually lie in this range from 2200 to 2800. Okay, so if you wanted to do these things all numerically, this Python program does these kinds of measurements. So for example, here we're calculating the sample mean from that command. Here's the sample standard deviation. Here's the standard error of the sample means. Here's the command that's used to find that t-factor to this confidence interval. Here it's actually 1 minus the confidence interval, but this corresponds to a 95% confidence interval. And if you wanted to see what the output from that program looks like, it's given right here. So this is where all these numbers come from. The sample mean, sample standard deviation, standard error of the sample means, t-factor. The true mean lies in that range. And then these are all the frequencies corresponding to these different ranges. So this whole output comes from that Python code. All right, hopefully the steps that we did, at least by hand up here, Hopefully all these various steps make sense to you.